Our project is emissive display technology in aerospace applications in collaboration with Korry Electronics. Korry Electronics manufactures numerous aircraft cockpit control devices, mostly known for their switch technology. Their current display technology for their switches involve flashing LEDs on a static imprinted image or phrase when it's pushed, and we were tasked with replacing this display technology with a programmable emissive display and to integrate this new display into an existing Korry product. Emissive displays have numerous advantages to traditional transmissive displays, such as improved lifetime, wider viewing angles, and smaller form factor integration capabilities. In addition to this, having a programmable display greatly increases versatility for an individual switch, as it would no longer be bound to the static image originally imprinted on it. It could be programmed to display whatever the pilot desired. Our team worked with a programmable OLED display and wrote software to employ various switch use cases. And additionally, we designed compact PCBs to fit into an existing Korry switch, which enable the OLED to function as the switch's new display.
So our design starts off with our bitmap and switch logic program, which we use Arduino for. It communicates with the RP2040 microcontroller, and then that drives the SSD 1331 OLED drivers, and then with that we're able to put it on the OLED screen. We use SPI communication to communicate between the microcontroller and the OLED itself.
I can continue on the software. So using the SSD 1331 driver, as Jesus mentioned, we were able to put a bitmap into that driver, which was able to print out images such as the Korry logo, as seen in our demo video, shown later in this video. We will also use the SSD 1331 driver to display other text and in color as well as different brightness, as seen in the images in this software box right here. You can see that the autopilot can be programmed to either bright or like a dim mode, as well as different multiple colors as demoed in the on-off switch, which shows green or red. Using this driver, we were able to efficiently write code that showed different use purposes for this prototype.
So the OLED display that we chose was a 0.95-inch diagonal 96 by 64 pixel full color OLED display. To power this display, we developed a PCB driving board for it that makes use of a step-up converter that amplifies the 3.3 volt signal to around 13.5 volts for the VCC. It connects all of the SPI communication to the vertical header on it, and also powers VDD at 3.3 volts into the OLED board. The power delivery into the switch itself makes use of 3 pins connected to the interior, one being ground, one being the 3.3 volt, and the last one being a GPIO port. The switch's internal logic is able to supply either 3.3 volts or ground to the GPIO, and there is hookup wire soldered to the connectors between the various PCB boards that allow for the power, ground, and the GPIO to all be connected together internally.
Yeah, okay. So we needed a microcontroller to fit inside our switch cap. And initially we were thinking about going with an STM32 microcontroller for prototyping purposes, but we realized it was too big. The space constraint that we had was 24 millimeters by 18 millimeters, so we opted for an RP2040 microcontroller, which is 7 by 7 millimeters. And our design is pretty standard for the data, according to the datasheet, and we just stripped down to the pins that we needed.
Going off what Chandler said for the custom microcontroller, we also chose the RP2040 for the built-in USB controller and built-in SPI controller, our primary interface for the microcontroller to SPI board. As he was saying, we scripted down to the bare essentials. So we mainly have USB for the connectivity and programming. We have a 16 megabytes of flash memory. And we have a 12 megahertz crystal oscillator, which allows the board to run at a clock speed of 125 megahertz internally. With the space constraints, we were able to have 5 extra GPIO pins for extra connectivity, for which we've only implemented 1 for now, but there are more if we need to use it. We manufactured the PCBs, both the OLED driver and the microcontroller, through JLC PCB with assembly. The microcontroller specifically has double-sided assembly since we are such limited in space constraints.
So for the adjusted switch cap, the original model, the cap contained a spring base as well as a flex PCB for LED backlighting. With our adjusted model, it still integrated the spring base to utilize that pushing mechanism, but now had to house in the custom microcontroller and OLED driver PCBs that we created. The adjustments that we made were at the top of our cap, where rather than a covering, we used a hole so that the PCBs could be inserted from the top. The base of the cap was stayed the same though to match the dimensions of this original Korry switch model. Some additional features we added was a transparent screen protection in order to protect the OLED screen when pressing the button, as well as USB access hole for programming in order to have easy programming access rather than taking everything apart.
With all that in mind, we have connected them all together into a fully functioning switch with a programmable display. Shown right now is the demo video of that switch in action, changing between on, off autopilot, dimmed autopilot, and the Korry logo, only being powered by the 3.3 volt and the ground supply, with the internal GPIO connection being made.